Here's some of the stuff that we've already talked about in class, but I wanted to make sure that anybody was absent or didn't take good notes had a good place to get some of this information. So when we talk about work, physics uses the term work slightly differently than you're used to in everyday life. The way I like to define work, there are a lot of different really terrible definitions of work out there on the internet, in textbooks, in just examples in physics. But the best way you can really think about how physicists interpret the term work is the idea it's how effective an outside net force is at changing the state of motion of the object. We need to be able to, it's how much it affects that change. So we think of positive amounts of work. If you're speeding something up, if you're lifting up, if you're compressing a spring, if you're doing something where you are causing the amount of energy to increase. Negative work is if you're slowing or lowering or releasing or doing something like that to an object. So that'd be the way it's calculated. The way you calculate it directly, when you know that force and you know the displacement, you multiply the two together. But they're vectors, so the way that you multiply them together is through what's called either the dot product or the scalar product. So you multiply those two things together. So you multiply the force, which is a vector, multiplied by the displacement. And when you multiply those two vectors together, the result that you get is dependent on the magnitude of each vector, the magnitude of the force, how much force there is, how many newtons of force, and the displacement, how far it's moved in meters. But you also need to include the angle between them, because if there's an angle, only part of the force is causing the displacement, or is related directly to the displacement. And so the way you calculate that is say work is equal to the amount of force multiplied by the magnitude of the displacement multiplied by the cosine of the angle between them. And so you get a maximum where the two things are along the same line and they're in the same direction. So theta is 0. You get a minimum or 0 whenever you get 0 whenever they are perpendicular to one another, and you get a negative answer whenever they're in the opposite direction. So imagine like an object is kind of rolling towards you and you push on it to stop it. It still moves, let's say it's moving to the right initially, you push to the left trying to slow it down, and so the force is to the left, the displacement's to the right until it comes to a stop. And so the angle between those two would be 180 degrees. The cosine of 180 degrees is -1. So the units that we use in the SI system for energy and work is just kind of related directly to energy, is the joule. And 1 joule is a Newton meter or a kilogram meter squared per second squared. So instead of writing Newton meter or kilogram meter per second squared, joule is used enough that it gets its own name. Now, in terms of other types of energy, 1 kilocalorie, capital C calorie, is 4,184 joules. A kilowatt hour, which if you ever pay a power bill, is you are somewhat familiar with, it's 3,600,000 joules. 1 electron volt, which is very useful in certain types of chemistry or atomic or nuclear physics, is related to the charge of the electron, 1.6 times 10 to the minus 19th joules. An erg, which often gets used in the CGS system, is 10 to the minus 7th of a joule. And a ton or a kiloton of dynamite. So 1 ton of dynamite is 4.2 times 10 to the 9th joules. So when they're talking about the explosiveness, the energy released in a nuclear explosion, they'll a lot of times use tons or megatons or kilotons or gigatons of dynamite. Now when we're talking about energy, the way I like to define it, as we discussed, is the ability of an object to cause change in itself or its surroundings. So instead of that circular definition of, work is the use of energy and energy is the ability to do work, we're directly linking energy to some kind of a change. The main categories of energy that we really divided into are kinetic and potential. Kinetic energy is the idea of motion, or even on the smallest level, the vibrational motion or random motion of objects that are at a different temperature, and then potential energy, which is stored energy. So kinetic energy, we're going to use capital K for that. Different textbooks will use different things. I'm just going to use the symbol capital K. And for normal objects, it's just the mass and the velocity. So the kinetic energy is 1/2 mv squared. That's related to how much it takes when you're accelerating something. I'll show you where that comes from in class. And when you have a bunch of smaller objects that are moving randomly, we call that thermal energy, but it's just another form of kinetic energy, one where we can't easily plug in 1/2 mv squared. Potential energy, we're going to use the symbol U. Some textbooks use PE. There are all kinds of different things like that. But I don't want to confuse too many things. This is an older nomenclature, but we're going to use capital U for potential energy. And when we do things, at first we're just going to use gravitational potential energy, and we'll have a subscript to define that. So gravitational potential energy is the weight of an object, mg, times the height it is above a certain zero, and you get to define what that zero is. But we can also look at potential energy of springs, what we call elastic potential energy, bending objects, things like that. Chemical potential energy, like in food or gasoline or things like that. Nuclear potential energy, what's happening inside the nucleus of the atom and if there are ever any changes there, etc. There are many different forms that we can use to describe potential energy. And so this comes back to the work energy theorem, back to one of my old definitions of work, is looking at what happens to the total amount of energy. So work is related to how much it can affect something, and so that's going to be the change in energy. So the work will be the change in kinetic plus the change in potential. A lot of times in textbooks, they leave out the change in potential. But what's happening is work is related to the amount of energy gained or lost in a system.